Hi, everybody. Welcome to Chapter 14, which is entitled The Internal Processes. So this chapter is quite long. There's a lot of material to cover, so I'm actually going to divide it into three parts instead of one or two. So this chapter is all about the internal processes, what's happening kind of beneath the surface of the planet, and how that affects what's happening on the surface of the planet. Here we have a picture of a caldera from Volcanoes National Park in Hawaii, which I got to visit, which was pretty cool. So this chapter will be all about that, and then we're going to talk about the external processes for the rest of the semester. So first we want to talk about a little bit what the planet looks like below the surface. So we have the lithosphere, which is the rigid uppermost layer of the planet, which we'll spend the rest of the semester talking about. This includes all of the crust and part of the mantle. Then we have the asthenosphere, which is the spongy, flexible layer underneath the lithosphere. And so the lithosphere floats on top of the asthenosphere. And this is important to know because we're going to talk about plate tectonics and how tectonic plates move. And so they are floating on top of that asthenosphere. So the theory of plate tectonics is that the lithosphere is divided into plates. And we can see where these divisions occur. We can see them quite well. And this includes the continents and the seafloor. So it's not just the continents that are moving, but it's also the seafloor as well. You can see this image right here. The Antarctic plate includes Antarctica, but also all of this seafloor around it. So continents and seafloor are often on the same plate, not always, but often. And these plates are moving very, very slowly. Again, we talked last time about geologic time, right? These plates are not moving super fast. They're moving very, very slowly. And sometimes we feel that movement when tension builds up via earthquakes, which I'll talk about a little bit later in this chapter. And these are driven by convection. So we've talked about convection several times already in this semester, but these kind of big loops of heat that are circling around, that are pushing the crust apart in certain places, which are called divergent boundaries, which I'll talk about, and pushing them together at other places, which are called convergent boundaries. So the theory of plate tectonics is the movement and interactions of plates that creates landforms. And tectonics just literally means building, right? It's a way that the planet is constantly building new landforms. So here is another drawing of the lithospheric plates. So we can see here the San Andreas Fault, which is probably the fault that we know best. There's a tiny little plate over here called the Juan de Fuca plate, which is being kind of eaten by the North American plate. Eventually that will disappear. We have these mid-Atlantic ridges where the plates are pulling apart and we're getting some new crust formed. We're going to talk a little bit about the Ring of Fire, which is this region around here. These are kind of gigantic convergent boundaries where you're getting lots and lots of earthquakes. Most of the earthquakes in the world occur in this Ring of Fire area. So they used to talk about continental drift. That was the previous theory before plate tectonics, which is not actually true, but it was pretty close. So Alfred Wegener in 1912 came up with a theory of continental drift. There he is right there. And he saw that all the continents kind of fit together, right? And we can see this here is an image of South America and Africa, and you can imagine how North America would fit in there. He noticed that all of these land masses must have been together at one point, and he thought that they had drifted apart. His ideas were heavily ridiculed. People couldn't really comprehend how these massive landmasses were moving. But he was almost correct. He just didn't realize that entire plates are moving. He thought it was just the continents that were moving, but the theory of plate tectonics lets us know that entire plates are moving, not just the continents. So this is the most recent supercontinent on our planet, known as Pangaea. There have been multiple supercontinents on our planet. These plates are coming together, forming massive supercontinents, and then they'll break apart, and then they'll come back together again. And again, we're talking about very long time scales. Pangaea happened 200 million years ago. You can kind of see when you look at this, and I'll show you another picture as well, like here is kind of South America, North America, here is Africa. You're going to actually, one of the short videos that you're going to watch outside of lecture is kind of what they think this is going to look like in the future. But again, very, very slow time, right? We're not going to see any of this in our lifetime. So there is another rendition looking at how current nation states would kind of fit into this Pangaea. So here you have most of Africa, South America, North America. Mexico is a little bit broken apart here. India kind of fits in right over here. And so how do we know that the continents have moved? How do we know that these plates are moving around, right? We can see little bits of movement, but like, how do we know that they came apart 200 million years ago? The first is fossils, right? So we can look at fossils that are millions of years old, and we can find the same fossil in southern South America that we find in southern Africa. And we talked about speciation before, and so we know that these guys are like way too isolated. They must have been connected at one point in order to have that same species there. The next is glaciation, and we'll talk a lot about glaciers, but we have parts of our planet that show evidence of glaciers that are much, right now, much closer to the equator. They would not have glaciers on them, so we know that they must have moved at one point. So again, we can see how they fit together, right? This area was at one point all covered with glaciers, and now we can see evidence of glaciation here throughout southern Africa all the way up to the equator, right? And so glaciers would never reach that far, and in India. We also have similar mountains. So the Appalachian Mountains and the British Isles and Chaldean Mountains are all part of the same ancient mountain chain. We can look at them and see that they're made in the same fashion. They're made of the same materials. So at one point, these guys were all together when those mountains formed. And there you can see the rendition of when they were all together, what they look like, and when they formed. We also have clues from the seafloor, and on the seafloor, when you have a divergent boundary, a boundary that's pulling apart, you're getting magma that comes up and you're forming new crust. So we can use sonar data, we can look at trenches and seamounts and mid-ocean ridges, and we can see that earthquake patterns lined up. We can tell that this crust is the same as this crust is the same as this crust, and we can see this pulling apart that's happening. Also through rock samples, we can look at the age of the rocks. We know that this rock and this rock are the same age. They are the same composition, and they also have the same magnetic polarity. So a couple of times, more than a couple of times, our planet has switched magnetic north. And so right now, if you have a compass, right, it points to magnetic north. The poles have swapped that magnetic polarity. We're not exactly sure why, but when rock forms, it will actually, some of the minerals in the rock will actually line up based upon polarity. So we know when these different shifts occurred, and so we can tell, we can look at these reverses in magnetic polarity also to use it for aging. And again, we have these symmetrical patterns moving away from the mid-ocean ridges. And all of this lets us know that the seafloor is moving too, not just the continents. And so we can look at the age of the seafloor. The youngest of the seafloor is closest to these divergent boundaries where it's pulling apart, and it gets older as it pulls away. Here's another divergent boundary down here. And so we want to talk about how Pangaea, that supercontinent, broke apart. So we had these rift valleys that opened up in the land, right? So these lands were connected at one point, but through this pulling apart, you had this rift valley that came in. As those plates spread apart, new crust is formed along those ridges, right? So we have this pulling apart that's happening, this magma that's coming up and forming this new crust. That new crust is thinner. It's basaltic. It's a volcanic rock. And so these Great Rift Valleys are formed. We have one being formed right now that we can see really well in Africa, which we'll talk about. And then you have ocean water that just comes in and fills these low-lying areas. We have a lot of water on our planet, so this water just, as soon as it opens up and there's a path for it, the ocean comes in and fills it in. And so today, most divergent boundaries are on the seafloor. We have a few that are not on the seafloor, which I'll show you, but most of them are in low-lying areas. There's been enough pull apart happen that seawater has come in and filled in that area. So these mid-ocean ridges are where the most recent crust has formed. So there are 3 types of plate boundaries. And I don't want you to get these confused with types of faults because we're going to talk about types of faults later. But we're talking specifically right now about plate boundaries. So we have these huge plates. And so what do where they're connecting look like? So the first one is a transform boundary. And this is where plates are sliding past each other horizontally. We can see those because we can see how this trench was here and this trench was here. And now they're being pulled side by side. If you could see my hands right now, this is much easier to teach in a regular classroom. So transform is plates sliding past each other horizontally. Then we have divergent plates, which is where plates are moving away from each other, which again, right there. And so that's where that new seafloor is happening, where you get this pulling apart, the magma is coming up to kind of fill in that gap, and you're getting this new seafloor. And then the last is convergent, which is this right here. So in this picture, you have ocean crust, which is heavier and denser, being subducted underneath continental crust, which is lighter. And so here with a convergent boundary is where you get a lot of these landforms that we're so familiar with, such as volcanoes and mountain chains happening. So as this plate is subducting underneath, you have it's melting and you have pockets of magma that are rising. We're going to, after the break from the first part of the lecture, the second part, we're going to talk about volcanoes. So again, transform boundaries, I'll go through each one of them. There's very little vertical movement. There's no mountains created. We're just sliding past each other. They're usually small and perpendicular to divergent ocean boundaries. We have a few longer ones, but generally speaking, these are pretty small boundaries. And so the San Andreas Fault is that type of boundary. And so when we get an earthquake on the San Andreas Fault, what's happening is that a lot of pressure is building up as these guys are sliding past each other, and the pressure is too much, and all of a sudden it slides really quickly, and that gives us our earthquake. And they tend to be rolling earthquakes. And so the last major one we had in San Diego was the one that happened on Easter Sunday quite a few years ago now, and it kind of felt, it was my first earthquake that I experienced moving to Southern California, and it kind of almost felt like I was on a boat and kind of going over waves, right? It's not these kind of really shaky, violent earthquakes. They can still do quite a bit of damage, but they're more of these kind of rolling earthquakes. And so we can see here the offset of the San Andreas fault, right? We can see here you have this drainage of Wallace Creek, but this plate has moved so much that now the old drainage is here, right? These guys used to line up, but because they're sliding past each other, we can see an even older one right here, these things are constantly moving. So with the San Andreas Fault, we can see that movement. This happened over quite a long period of time, but we can see it in very small chunks. The next type of plate boundary I'm going to talk about is a divergent boundary. And so again, this is where it's pulling apart. happens at mid-ocean ridges and also continental rift valleys. So places where it hasn't pulled apart enough that ocean water has filled it in yet. We get non-explosive volcanoes. We just kind of get this slow rising of magma to the surface, but not those kind of hugely erupting volcanoes that we see with convergent boundaries. So just remember, divergent is pulling apart of the plates. And so we get earthquakes there too, but they're pretty shallow, focused earthquakes. So the Great Rift Valley, which I've had the pleasure to visit in Ethiopia, is where the pulling apart is happening, right? So right now we could see we have some pulling apart here that's happening. The Red Sea is a result of that, but eventually these are going to pull apart enough, and over here as well, that seawater is going to fill in all of this and separate out these land masses, right? So you could see here, this is the Great Rift Valley. It's being pulled apart. Here is your newer crust down there, and eventually this will fill all in with ocean water. We can also see divergent plate boundaries on other parts of land. Here are ones in Iceland. Iceland has a divergent plate boundary that goes right down the middle of it. So you could see here this pulling apart. It's not like the ocean one where you have kind of all that magma immediately rising to the surface, but it is pulling apart. There's also lots of kind of geothermal activity in Iceland and volcanoes as well. So the last type of plate boundary is convergent plate boundaries, and this is where you have two plates colliding. And so these divergent boundaries create crust, convergent boundaries destroy crust. So again, as the pulling apart was happening with the divergent plate boundaries, you're getting magma that rises up and creates new crust. With convergent plate boundaries, this ocean crust is going underneath this continental crust and is kind of being eaten by it. It's going to remelt. So there are three types of convergent boundaries, depending on what type of crust is involved. So again, we have ocean crust, which is thin, heavy, and dense, right? It has the weight of the water on it, so it's very thin, but it's very dense. And continental crust is very thick. Think of it as light and fluffy. And so here are your three types of convergent plate boundaries. The first one is when you have an ocean plate colliding with a continental plate. And so that ocean crust subducts. It is heavier, so it goes underneath that continental crust. And so here we can see that first type, you have an ocean continent boundary. So this ocean crust is going to go underneath, and it is going to subduct, and you're going to have some new magma being formed. Some of it is going to rise up and create volcanoes and mountain ranges. The second type is ocean on ocean. And so one plate is going to subduct under another one. And again, you can get kind of an island arc that is formed here. And the last is continent on continent. And so there's no subduction that's happening here. When you get these two plates that push together, everything gets pushed up. Everything kind of crumples together. This is how the Himalayan mountains are formed. Some of the tallest mountains in the world, right, are formed from this continent and continent collision. And so subducting crust, as the crust goes underneath, it traps in water and gas that then gets heated. The crust melts as it gets deeper and hotter. That molten rock will rise up, and it results in very deep focus earthquakes that happen well below the surface, not shallow ones that are happening up here, but they're happening very lowly. It results in ocean trenches. Here's a trench right there that is being formed from this ocean crust being pushed underneath this continental crust. Also volcanic arcs that are active volcanoes, right? So you see this mountain range here. You have this magma that's rising up, pushing this stuff up, creating this mountain range. Oops. And And so again, here's another picture of it, right? Here's a trench. You're going to have this plate, this ocean plate that's subducting underneath, this other ocean plate. And again, you're going to get, you can get islands, right? So when you have a continent, you're going to get a mountain range. When you're happening with two ocean plates, you're going to wind up with some islands that are forming. And so most convergent boundaries are subduction zones. So the vast majority of them where you have two plates coming together, one is subducting under the other one. The case where you have two continental plates coming together and mountains rising up, like you do here in the Himalayas, is more of the exception. Most time you're having some type of subduction happening. And so we're going to come back in the next part of this chapter and talk about volcanoes and volcanic arcs that happen from this subduction.